Okay, so I know that in the other videos and materials you've read and seen a whole bunch about radioactivity already and nuclear energy. I'm gonna, in this video, talk just a little bit more, put some details together, and hopefully help you out with the homework. Just to try and talk about some of the details and put it all together. So this graph is a really interesting graph. It's got a ton of information in it about the structure of a nucleus and about what causes it to change in different types. The graph is showing on the horizontal axis the number of protons in the nucleus. So starting at low number of protons, going up to a high number of protons, and low numbers of protons means it's a small atomic number, elements like hydrogen, helium, and lithium. And high number of protons means it's one of the really heavy ones, up in the gold and silver and uranium and other big elements like that. And then this axis is showing the number of neutrons that are in the nucleus, um, also counting upwards. And you can see that in general, you have the more protons you have, the more neutrons you have. And the colors on this graph are showing, each little square is showing a different kind of nucleus. And the kind of nucleus is determined by just how many protons there are and just how many neutrons there are. So this spot right here that I'm pointing at corresponds to an element, an atom with about 35 protons and about 50 neutrons in it. And you can see that it's colored blue, which means that that particular kind of nucleus tends to decay using beta minus decay. We'll talk about what that is in a minute. So I'm going to go back. I'm going to come back to this graph. I'm going to put a copy of these notes below the video. I want to talk about some details here. So the nucleus is made up of neutrons and protons, and they are stuffed together in an incredibly small space. And I do mean incredibly small. Like the typical size of a nucleus is about 10 to the minus 15 meters in diameter. Very, very small space, unimaginably small space. The protons are positively charged. The electric force between those positive charges is repulsive, meaning it tries to push them apart, and it's enormous because they're all the same positive charge, pushing each other apart, and they're really close together. Put those two things together and you've got a force that's trying to push them apart that's enormous. Okay, neutrons are neutral, hence the name, so they don't have electric charge. So they don't have a force that's trying to push them apart. And because they're in there in the nucleus, they partially shield that electric force between the protons. So part of the reason that the nucleus is stable is because the neutrons are there and they're reducing the effect of that enormous electric force between the protons. But there's also another force called the strong force. Why is it called the strong force? Because it's really strong. Physicists are sometimes not particularly imaginative in their names, and when they realized that there was another force in addition to electricity going on inside the nucleus of atoms, they imaginatively called it the strong force, because they knew it had to be much stronger than electricity to explain how the nucleus stayed together. So it also helps keep the protons together, but it has a very short range. So basically, you can't feel the strong force at all if you're outside the nucleus, outside of that 10 to the minus 15 meters. But if you're inside it, it's a very large force, and it's big enough to keep the protons together, even though they would, on their own, blow themselves apart because of the electric force being so enormous. So there's a really complicated interplay between all those forces, between the protons blowing themselves apart, the neutrons shielding it, and the strong force trying to glue them all together. And because that's complicated, there's lots of different ways to balance those forces to get a nucleus. That's why there's lots of different kinds of atoms and isotopes. So let me go back up to that graph. So the reason there are so many different ways to make a nucleus is because there's lots of different ways to balance those forces to get a nucleus that stays together. Interesting thing is that all of these black ones here are stable. those are ones that, left alone, will just stay there forever. They won't really change because that particular arrangement of the neutrons and protons and those forces will hold itself together. But if you go off of that line just a little bit, you'll find that it's not stable. Over time, those forces that are not quite balanced will eventually change the nucleus into a form that gets it closer to being on that black line. So left by themselves, all of these nuclei that are not on that black line will slowly change themselves into ones that are on that black line. This line right here is showing where the number of neutrons and protons is the same. And you can see that kind of you want the number of protons and neutrons to be the same. That's more true down at the bottom when they're very small nuclei. But as you get bigger, you want to have more neutrons than protons in order to be stable. That's why it's up here above that line. And that's because when you get extra neutrons, you get more of the shielding effect, canceling out that electric force. So let's go back down here. So some of those waves are stable and some are not. The not stable ones will eventually change themselves to become stable. So let's talk about some of the ways that they can change themselves. So one way, a neutron can turn into a proton and electron. This is a little bit weird. So these particles can change themselves. And effectively what happens is you have a neutron that was in the nucleus, and it spontaneously changes itself into a proton that stays in the nucleus, and an electron that gets spit out and goes flying away. That's called beta minus decay. The effect of that decay would be to move the atom down and to the right on that graph. So let's talk about that. So beta minus decay are these turquoise ones. Let's say we're right here. Draw a little spot. We've got extra neutrons, more neutrons than protons. And if you take a neutron and turn it into a proton, that's going to make you move down because the number of neutrons will decrease. You turn it into a proton, that makes you move to the right. And then an electron gets spit out of the nucleus and goes flying away. So the effect of that decay, let me draw another dot right there, is to cause the atom to move down and to the right, that way. Because the neutron going away moves down, the neutron turning into a proton makes it move right, the electron gets spit away. And the reason we know of the existence of this kind of radiation is because we detect those electrons flying away from the atom, and we can see their effects when they hit other things. So that kind of decay causes you to move down and to the right, and you can see that for all those blue things, moving down and to the right gets you closer to that black line that's stable. Okay, then next one. A proton can turn itself into a neutron and a positron. Neutron and a positron. A positron is just like an electron, except it's positively charged. So it's a really small particle that has a positive charge, and it will also get shot out of the nucleus. That's called beta plus decay. And it moves an atom up and to the left on that graph. Let's go back up there and see how that is. So we're talking about these orangish ones. And let me draw a spot right there. Let's say this spot right here undergoes beta plus decay. So you have a proton turns into a neutron. So that means the number of protons will decrease. The number of neutrons will increase. So you move that way. And then a positron gets kicked out of the nucleus and goes flying away. That causes you to move up and to the left. And you can see that for all of these orange colored ones, that kind of decay is going to make you move closer to the black line that's more stable. So those two are by far the most common kinds of radiation that you see. You can see all of these nuclei that are turquoise colored undergo that kind of radiation, and that causes them to become more stable. And all these ones that are orange colored undergo beta plus decay, which causes them to become more stable by moving up and to the left. And again, we know about these kinds of radiation because we can detect those particles flying out of those nuclei, and their effects on other things. Let me talk about alpha, which is, no, I'll talk about, I wrote them in order. Let's say the nucleus just spits out a proton. It doesn't change anything, it just kicks it out. That's called proton decay, obviously. So if you spit out a proton, that's called proton decay. If that means you're just decreasing the number of protons without changing anything else, that makes you move left on the graph. This is a less common form of radiation. It happens with these smaller ones down here. It's kind of a reddish color, and if you decrease the number of protons, that just makes you move to the left without going up or down. But that does move all of them closer to that stable line. Neutron decay is the reverse process where you have a bunch of extra neutrons. One of them gets kicked out and spit away from the nucleus. That makes the whole thing move downward, because the number of neutrons will decrease. So that also makes those move closer to that stable line. And you can see that's also not a particularly common form of radiation. And it tends to happen for the very small ones. So those happen when you have a lot of excess protons or when you have a lot of excess neutrons and the nucleus just kicks them out in order to get closer to that stable line. And then second to last one to talk about is if the nucleus spits out 2 neutrons and 2 protons together. That's called alpha decay. And that was one of the earliest forms of radiation that was discovered because we were able to see the effects of those particles spitting out of the nucleus. So if you kick out 2 neutrons and 2 protons, and this is these yellow ones that are up here, it tends to be bigger ones that do that, that's going to cause you to move down because you lost 2 neutrons and left because you lost 2 protons. That's causing these ones that are up here to move that way, which is closer to this stable region. You can see that above this line of about 82 protons and 126 neutrons, there aren't any stable arrangements, and you just have to get down this direction to become stable. These names, alpha and beta, and one of the other videos talks about gamma decay, those names come from when they were discovered. So alpha decay was the first one, beta decay was the second, gamma was the third, and that's because the order of those letters in the Greek alphabet is alpha, beta, gamma. The next kind of radiation would be delta, if there was one. So those are the different kinds of radiation, and those are happening because the parts of the nucleus are either changing themselves or spitting themselves out of the nucleus in order to get into a configuration that is more stable than it was. That happens because there's lots of different ways to arrange all those particles to get a nucleus, but not all of them are perfectly stable. All right, and then one last thing that can happen, which is really important when we're talking about nuclear energy, is that the nucleus can just split itself into 2 much smaller pieces. That's called fission, and that is the basis of nuclear reactors that are in use today in power generation. And that also causes you to move down and to the left on the graph because you've just reduced the number of both of them. That is a less common form of radiation. It's these really light green ones up here. And those are the ones that you've heard of as being involved in nuclear energy and bombs like plutonium and uranium and stuff like that. So now what I want to do is talk a little bit about the homework questions. And I'm not going to solve them for you here. I'm going to talk a little bit and give you some more background information. The solution is in the PDF that I'm attaching in the assignment. So you can read it there and you can use that when you're constructing it yourself. But I want you to try and do this on your own. So the questions are, suppose you have a Geiger counter, which is a device that measures radioactivity. It measures the activity of a sample of a particular radioisotope to be 160 counts per minute. So this is this thing that you might have seen in movies or other places where you've got a device that you stick into a radioactive thing and it goes tick, 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 and it counts how many times it measures something hitting it. So you measure that it's counting 160 of those things hitting it every minute. And then 8 hours later you return and you measure it again and you find it's only measuring 10 counts per minute. So you're getting less radiation from it 8 hours later. And the question is, what's the half-life of the sample? And it turns out that it's about 2 hours. and you're going to figure out how to get that. The idea of this is that because that sample is undergoing radioactive decay, it is becoming more stable. Every time one of those atoms that is not totally stable decays, that causes it to move closer to that stable line, and it causes a higher proportion of the atoms that are in that sample to move closer to that stable line one way or another. So at first, you're getting 160 counts per minute because you've got a whole bunch of them that are not on that stable line, and so they're decaying, getting themselves closer. But over time, you have more and more of the particles that are in your sample that are stable, and fewer of them that are not stable, which means the number of counts that you're going to get every minute or every second or whatever is going to decrease. And the question is, in the homework question is, well, how long does it take for half of them to have done that? And it turns out that it's about 2 hours. Second question, how many atoms are in a 1 gram sample of sodium-24? It's about 2.5 times 10 to the 22nd atoms. This is an Avogadro's number problem. You're going to need to look up what is the atomic mass of sodium-24, use the mass of the sample, and you figure out how many atoms that is that must be there in order to add up to a total of 1 gram of sodium-24. This is a really important and difficult, I think, to visualize thing about atoms. They're small. They're really, really, really small. And there are a lot of them in any sample. A 1 gram sample of sodium-24 is tiny. A paperclip is 5 grams. This is a small amount of stuff, and there's 10 to the 22nd atoms in it. That's huge. There's only 10 to the 9th people in the world. It's a lot. And that means that the numbers involved when you're talking about atoms are really big and really small. Really big for the numbers and really small for the sizes. Difficult to visualize, I think, and important to think about what that means. Okay, and then the last question in 2 parts. How many radioactive decays will happen in 1 day for the following 2 samples? So you've got a gram of iodine-131. So you're going to need to find out how many atoms that is using the same process that you did for number 2. How many atoms is that? Given that the half-life of the sample is 8 days. So that means after 8 days, half of that sample will have been turned into something that's not radioactive. And it turns out that in 1 day, 3.8 times 10 to the 20 atoms will decay. That's a huge number that will decay, and it's not even half of them. And in part B, 1 gram of tritium. So we've got a different element that has a half-life of 12 years, so a much longer half-life. It takes longer. That means a smaller percentage of them are being transformed every second. And but it turns out that it's 3.99 times 10 to the 19 atoms that will decay in 1 day for that particular sample, and you're going to figure out how to get that. So something that I find really fascinating is thinking about why is it that radiation obeys rules like a half-life. Half-life, to me, it just sounds kind of strange. Well, why would you talk about how long it takes for half of it to disappear? The interesting thing about radiation is that because all of the atoms are independent of all the others, they don't really affect each other. So one of them decaying doesn't affect the decay of the others. This is for normal natural radiation. So each atom obeys its own little probability rule. Every second, there's some probability of decaying, and that probability is relatively small usually. And there's some probability of not decaying, which is relatively large. So there's a probability of not decaying. So since there's a lot of atoms in the sample, and it's very big, that means that every second you'd expect the number times the probability to not decay, atoms to not decay. And 1 minus that to decay. So like if you had 1,000 atoms to start with, and a 90% probability of not decaying in 1 day, or 1 second, or whatever amount of time you're talking about, you would find that after 1 day, on average, there would be 900 left. And then that 900 that's left will obey the same rule. It will also, 90% of it will be around the next day, and 10% of it will disappear. So to find out how many are there after one day, you multiply the starting number by 0.9, you get 900 left. To find out how many are there after 2 days, you take that number, 900 times 0.9 again, and you get 810 left. And that works because each atom is independent of all the others. It doesn't matter how many are there. The percentage will drop by the same amount each time. So you just keep multiplying the current number of atoms by the probability of not decaying. You get the number of atoms that have still not decayed. So mathematically, processes that follow that kind of rule are called exponential. In essence, it is that the proportion of that decay in each second is always the same, rather than the number that decay in each second being is the same. So you can see that in the first day here, 100 decayed, and in the second day, only 90 decayed. That's that decrease in the number of counts that happens with your Geiger counter. So it gets less hot because fewer of them are decaying, because there's fewer of them there to begin with. But the percentage drops by the same amount each time. So let's follow that through. If the probability of remaining around for, I keep saying 1 second, let's say 1 day. 1 day is 90%. How long does it take to lose half of the sample? So we would follow that progression of saying 1,000 times 0.9 is 900. Then multiply by 0.9 again, and you get 810. And we're just going to keep going until we get to 500 and count how many days did that take. So let me do that with a calculator. And I've got, so after we start with say 1,000 grams of the sample, or 1,000 atoms, 90% of them decay on the stay around on the first day, and 10% decay. So you've got 900 left. Then you do that again, and you get 810 after 2 days. Do it again, you get 729 after 3 days. 656.1 after 4 days. 590 after 5 days. 1, 2, 3, 4, 5. 0.9. 531 after 6 days. I think we're going to get it on this next one. Times 0.9. 478. We've finally dropped to 1/2, somewhere between 1, 2, 3, 4, 5, 6 days and 7 days. There's a way of figuring out exactly how many it is. So it's more than 6, less than 7. So the half-life is about 6.5 days. This kind of process, once you know what half-life is, you can write down an equation to describe how many particles are there, or how many particles are there at some later time, saying, okay, the number at some later time is equal to the number that you started with times 1/2 to raised to the power, and it's to an exponent because you were multiplying a whole bunch of times, the amount of time that has happened divided by the half-life. So if you know the half-life, you take the amount of time that's happened divided by that half-life. That tells you how many times you have cut it in half. Multiply that by the number that you started with, and you will get the number that you've ended up with. So in our particular example, we started with 1,000 times 1/2 to the 6.5 days divided by the half-life, and you'll figure out how many are there later. So you're going to want to use a version of that equation, and more specifically this one, when you're doing those questions on the homework, especially that number 3. So if you ask yourself, what's the half-life? What's the amount of time this happens? And you can figure out the proportion that is still there. So I'm just going to show you that the solution to those questions is down here. And it's basically the same process for both of them. I'm not going to go through it, but you can look at that solution when you look at the PDF that's attached in the homework, and let me know if you have any questions. All right, good luck.